One way that we can find a power series representation of some function is using a form that we've seen in the past. We know that this is true. The sum n equals 0 to infinity, sum a, not a sub n, sum a, r to the n is equal to a over 1 minus r as long as the absolute value of r is less than 1. This was our geometric series. All right, now here's the idea behind this. If we have some function that we can get into this form, then we would be able to rewrite it as a series. Now, since we want it to be a power series, which generally looks like this, sum n equals 0, sum a sub n, x minus c to the n, notice if we compare these two, here a is a number in this case, a sub n is generally a function of n, so those two things are probably going to be somewhat related. And r sub n is our x minus c to the n. So when we're trying to do this, where the r is, we're going to want our x minus the center. So let's see how this works, and believe it or not, it's pretty easy. So I'm going to just say, write as a power series. And those are going to be the directions for the next 3, 4, 5 examples. Let's start out with something real simple. So let's say f of x was 2 over 1 plus x. Okay, something really straightforward. Now, to get it into this power series using this idea, we need to get it into this form right here. So a couple of things that we have to notice. There has to be a 1 in that position, and it has to be minus r, and r has to be where our x is because we wanted the x to be raised to a power. So this is almost exactly in the right format. All I'd have to do is rewrite that as 1 minus negative x. So see, now we have our a over 1 minus, that's our r, which means now we can plug this in. So f of x is equal to, the sum n equals 0 to infinity, a is 2, oh, by the way, in this case our center is 0. Yeah, I had to say that. We'd have negative x to the n. Now notice, we do need to clean this up a little bit. I can rewrite that as negative 1 to the n and x to the n. N equals 0 to infinity. So that's 2 times negative 1 to the n, x to the n. So notice this is a power series. There's our a sub n, our function of n, and here's our x minus c. Now in this case, I forgot to tell you we were going to center it at 0. Center it at 0, so we get x minus 0 to the n. And there we go. There's a power series representation for this function. Now, since it's in geometric form, we can kind of figure out where this is going to converge or diverge for what values of x, right? Because the absolute value of our r has to fall between negative 1 and 1. Okay, let's try another one. Let's do it slightly different. This one's going to be a little bit more work. Let's say our f of x is, I don't know, let's make it really ugly. 5 over 3 plus x, and let's center this time at 2. All right, so we got several things that we need to take care of. We need our center at 2, which means everywhere there's an x, I need an x minus 2. So that's the first thing I'm going to do is I'm going to set my center. So down here where there's an x, I'm going to go 3 plus x. I need that to be x minus 2. But I can't just put a minus 2 in there. I'm also going to put a plus 2. So there's my f of x. So now I'm going to put the r piece, the x minus 2 where I want it. I'm going to go plus the x minus 2. Think about that in parentheses. What I have left on the bottom now is a 5. Okay, so we're closer to what we want because we needed that x minus c right there where the x is. But now we got 2 more pieces we need. We need to make that spot a 1 and we need a minus. And it really doesn't matter what order you do this. To make this spot a 1, divide every term and every factor in there by 5. So if I divide everything by 5, divided by 5 plus x minus 2 divided by 5, we would get f of x is equal to 1 over 1 plus, I'm going to write that as x minus 2 over 5. Well, we're almost got it in the exact form that we need, except we got to put a minus there. So we're going to do the same thing we did last time. So f of x is equal to 1 over 1 minus negative x minus 2 over 5. Okay, so now that we have it exactly in our geometric form, I should be able to put this into a power series. So I'm going to say that our f of x is now equal to the sum n equals 0 to infinity. Our a is 1, r is negative x minus 2 over 5 to the n. So a over 1 minus r, so that's our r. Now generally we're going to put this in our power series form. Remember, we want all the a sub n stuff in front and then just our x minus c to the n. So I'm going to rewrite this a little bit. The sum n equals 0 to infinity. Let's see, on the top I have a negative 1 to the n, x minus 2 to the n, and on the bottom that would be a 5 to the n. So my f of x would be the sum n equals 0 to infinity, negative 1 to the n, 5 to the n, x minus 2 to the n. All right, that should model our power, that should model this function for certain values of x. Now, if you want to know where it converges or diverges, you do need to work on that, because remember, this was our r here. So technically, the absolute value of this has to be less than 1 to figure out where it's going to converge or diverge. Okay, so if you just have something that has this form, you might need to manipulate it to get it in there. You may even have to do something as complicated as maybe partial fractions to get it into a couple of terms. Let's take a look at another example of things that we can do to get stuff into the correct form. What if I said write a power series for f of x is equal to the arctangent of x? Well, from here you'd say, well, this isn't going to work at all. There's no way that this is going to work, because to put it into this form, I'm going to have this kind of a over 1 minus r. That looks absolutely nothing like it. And you're right, it doesn't. However, the derivative of this, f prime of x, the derivative of the arctangent, is 1 over 1 plus x squared. Now that does look a heck of a lot like this here. So to get it into that form, all I would have to do is write that as 1 minus negative x squared. So f prime of x would be, the sum, n equals 0 to infinity. A is 1, r is negative x squared to the n. Well, we're not done, because we can clean that up a little bit and put it in our power series form. I'll put one more line down here. So let's clean it up just a little bit. So f prime of x, n equals 0 to infinity. We can write that as negative 1 to the n. Power raised to a power, we multiply, so that's x to the 2n. The problem is, that's the power series for the derivative of the arctangent. I don't want the power series for the derivative of the arctangent. I want the power series for arctangent. So to find, this is the, we're going to have to integrate, right? So this is the derivative of the arctangent of x is equal to the sum n equals 0 to infinity, negative 1 to the n, x to the 2n. So to get to the tangent, I'm going to integrate both sides. Now, of course, if I integrate the left-hand side, that's easy enough. That's just going to give me the arctangent. So if I integrate the derivative here with respect to x, and I integrate this side, that should give me my answer. Well, this is just the arctangent of x. Over here, remember when we integrate power series, we just do it like we normally would. So this is going to be the sum n equals 0 to infinity. We're going to add 1 to the power, then divide by that power. So if we add 1 to that power, I get 2n plus 1. We divide by 2n plus 1. Now we do get an integration constant out there. Now this is where we need to know something about this function. So I'm going to pick something that I know off the top of my head that sounds really easy. I know arctangent of 0 is 0, which means if I plug 0 into here, I need to get 0 back out. So the arctangent of 0 is going to equal to the sum n equals 0 to infinity, negative 1 to the n, 0 to the 2n plus 1 all over 2n plus 1 plus c. Now, since every term here is going to have an x in it, right? This is all going to be 0, which means c has to be 0. So the arctangent of x is just the sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 all over 2n plus 1. Okay, now I didn't say it at the beginning again, I absolutely should have, that our c was 0. I keep leaving that off, but again, we see we have a power series and it's centered at 0. Now if you wanted to move that x off to the side so it fits the form, you're welcome to, but that's fine the way it is. So sometimes when you're looking to find the power series of a function and you're not sure, you may want to take a look at either the integral of that or the derivative of that may be helpful. Which brings us to our next example. Let's take a look at, what if I said our function was negative 1 over 1, let's go minus x. Let's go 1 over 1 minus x plus. Let me do plus. Okay, so again, if we were looking at this, you're like, well, that's close to the form to put this into a geometric series, but that's 1 minus x squared on the bottom. That doesn't quite fit. But you might notice that the derivative of 1 over 1 plus x is negative 1 over 1 plus x squared, right? I can write that as 1 plus x and negative 1, bring down the power, take 1 away from the power, that gives me a negative 2, which gives me that. Now, why would I want to do that? Well, if you look at this, I know the power series for this. So the power series for that, if I just rewrite it as 1 over 1 minus negative x, that's going to be equal to negative 1 plus x squared. So the derivative with respect to x, what's this going to be? Well, that's going to be the sum n equals 0 to infinity, negative x to the n, and I'm going to rewrite that so it's kind of in our power series form. N equals 0 to infinity, that's going to be negative 1 to the n, x to the n, negative 1 over 1 plus x squared. Now, notice all I got to do to get that answer is, well, take the derivative of this. And we know that taking the derivative of power series is very easy. I'll just write that on this side. We say that this is going to be the sum. Now, we're just taking the derivative of the x, so I get negative 1 to the n, nx to the n minus 1. Now, this doesn't start at 0 anymore because it doesn't exist at 0, so now that series starts at 1. There you go. So we have a power series representation of function. So just because, like we did with the arctangent, we knew the derivative of this. We knew that this was the derivative of something, so it's very easy to find the power series. So finding a power series using your geometric form, it can be very, very helpful. So if it kind of looks like something like this form or something you put into that form by using maybe partial fractions or just rewriting it, this is a great way to write a power series for some function.